Okay, so we will continue problems on chapters 7 and 8. Okay, so before we continue, did you face any problem with the concept of latent heat and sensible heat? If you want me to repeat anything, okay. So let us continue. Okay. A flat plate is to be cast in an open mold whose bottom has a square shape that is 200 millimeter by 200 millimeter. The mold is 40 millimeter deep. A total of 1 million millimeter cube of molten aluminum is poured into the mold. The solidification shrinkage is known to be 6%, which is a volumetric contraction, not a linear contraction. Aluminum has a 1.3% linear shrinkage due to thermal contraction after solidification. If the availability of molten metal in the mold allows the square shape of the cast plate to maintain its 200 millimeter by 200 millimeter dimensions until solidification is completed, determines the final plate dimensions. So this problem will deal with shrinkage and how we can know the final dimensions of our cast, final cast. Okay, so what we will do here first, let us do a small figure that will allow us to understand what is happening. So first, they are telling us that our mold has a base, a square base. Okay, so we have it like this. The dimensions of the base are 200 by 200. And as you know, we have two phases of shrinkage. Okay, we have first the liquid shrinkage phase, which is related to density increase and also formation of solid at the wall. Okay, this will cause a certain shrinkage during the first step. And after complete solidification, we have another shrinking phase. Okay. Now, during the liquid shrinkage, if you want, they told us that since we have availability of molten metal, we have this will allow the square shape of the cast to maintain its 200 millimeter by 200 millimeter. So what they mean by this, reducing in dimensions during the first stage will be just a reduction in height because the base will maintain its dimensions. So during the first shrinkage step, which is called in general liquid shrinkage, okay, you have that the dimensions are 200 millimeter by 200 millimeter, and they will not change in the first step. Okay, so in the first step, uh, I have what is called here before complete solidification. And after complete solidification, we have the thermal contraction shrinkage. Okay, so thermal contraction after solidification will be for all dimensions, but shrinkage before complete solidification will be only along the height. And in general, this will be precise in the given. As I will tell you this to avoid confusion. So what will be done is that initially, first we should find the initial height before starting of shrinkage. So H0. How to calculate the initial height H0? Please pay attention. The mold depth is not by force the initial height because you can if you don't fill completely the mold, then H0 will be different than 40 millimeter. So some common errors is to take that H0 is the depth of the mold. No, because it will depend on the amount of molten metal poured into the mold. This is why here to determine the value of H0, what should we use? What should we use in the given here to determine the initial height? Which information? Who will tell me how we can find the initial height? It's very simple. Read well the given. Yes, exactly. We will use the volume. We have that the volume of molten metal is 1 million millimeter cube. Okay, so we can say that volume of molten metal, volume of molten metal is equal to the base area, which is 200 times 200. Since the volume is provided in millimeter cube, then I will have all dimensions in millimeter. So 200 times 200 times H0 equals to 1 million. From this equation, you can deduce that H0 will be 25 millimeters. Okay. So as you can see, the volume of molten metal will not be able to fill completely the mold, but it will just fill until 25 millimeters. Okay. Now, this is the initial height. Now we have two phases of shrinkage. The first phase before complete solidification, okay, is 6%. Now it's very important here to notice something. We talk about two types of shrinkage: volumetric contraction and linear contraction. Okay, when they say here it's a volumetric contraction, this means that it represents the reduction in volume. Okay, so when they give you a volumetric contraction, you can say, you can use it as following: that V final is equal to 1 minus the volumetric contraction times, so let us put it volumetric contraction times the initial volume V0, okay, times V0, okay. So this is, if you want, I will call it V1 because it's after the first phase of shrinkage. So this is equal to 1 minus 0.06, okay, times V0. V0 is 1 million millimeter cube. So you can get in this way what will be the value of your volume just after phase 1, okay, and it will be equal to since this is it will give you, this is 94% of the initial volume, so you will get 940,000. Okay, this is the result you will have. Now, this is a millimeter cube, of course. Now, once you have calculated the volume just after the first phase, you will be able to calculate the new value of H1, okay? Because H1, since the base is not changing in dimension, so we can say that H1 is equal to V volume after the first phase of solidification over the base area, which is, so over area of base, so it's equal to 940,000 over 200 times 200. In this way, you get the value of H1. Who can give me directly H1 without doing all these steps? What can we do in other words? What can we do? Look, here, the variation of your volume is due to what? Is due only to the reduction in height, okay? Since the base is not changing in dimension, then the volume reduction will be equal to the percentage of reduction of H. Okay, so you can say since the base area is not changing, another method to get H1, okay, you can say then H1 is equal to H0 times 1 minus the volumetric contraction. Okay, and here if you want, here the volumetric contraction will be equal to the linear contraction of the height, because the contraction is only taking place along the height but not along the base. So here also you can directly say, since the base area is not changing, that H1 is H0 minus 0.06, so it's equal to 25, which is the initial height, times 0.94. Okay, so also this will give you the same result for H1, and the value will be in millimeter. Now, once we do this step, we still have a second phase of shrinkage, which is the thermal contraction phase. During thermal contraction, you will have variation in all dimensions, the base dimension and the height. So this is why, as I told us, that in the second step, we have 1% of linear shrinkage. Okay. Now, even if they gave us the volumetric shrinkage, we can deduce the value of the linear shrinkage. Why? Because we can write a relation between the volume V after phase 1 and volume V2. We can write it function of the linear shrinkage or function of the volumetric shrinkage. This will allow us to relate the linear shrinkage to the volumetric shrinkage in the second phase. Okay? So what we can say here, let us use first the information provided. What does it mean that I have 1.3% linear shrinkage? It means that each side of my final cast will be reduced by 1.3% at the final phase. Okay, so until now, after phase 1, what will be our dimensions? The base is still to 200 by 200, but now the height is reduced. Okay, so we have the value of a new height. So I will say after phase 1, I have that H1 is 0.94 times 25 millimeter, and I have that the base dimensions are still the same, so it is 200 millimeter for each side. Okay, now what will happen after phase at the end of thermal contraction? I will have new values for the base dimension and for H1. So the new values will be height at after phase 2 is equal to, since I have 1% linear shrinkage, this means that H2 is H1 times 1 minus the linear shrinkage. Okay, so it is equal to H1 times 1 minus 0.030. Okay, so this will give you the value of H2. So in total, H2 is equal to 0.94 times 0. So 1.3%, yani the remaining is 98.7. So 0.987 times the initial height, which is 24. So this will give you the final height after complete solidification and after thermal contraction. This is the value of H2. For the base dimensions, since it's a square, so each side, the new value of the side after phase 2 is equal to 200 times the linear 1 minus the linear shrinkage, so times 1 minus 0.013, so it's equal to 200 times 0.987. Okay, and then once you find the new dimensions for the three sides, okay, this is what was the question. You can find the new volume by multiplying h2 by a2 squared. Okay, now if they ask you calculate the total volumetric reduction, okay, what you do is you calculate the initial volume, you calculate the final volume, and you do the ratio. Then the total volumetric shrinkage will be 1 minus this ratio. Okay, and another possible question is to ask you, for example, what is the volumetric shrinkage during phase 2? Who can tell me what is the volumetric shrinkage during phase 2? How can I calculate it? Any idea? Okay, so let us solve it here. The volumetric shrinkage during phase 2, if I want to calculate it, what is the definition of volumetric shrinkage during phase 2? Okay, I have in general the definition of volumetric shrinkage is I will compare volume 2 to volume 1. V2 over V1, okay, is equal to 1 minus the volumetric shrinkage, okay, 1 minus the volumetric shrinkage 2 in phase 2. Okay, now V2 over V1 is equal to what? V2 is reduced because of the linear reduction for the three sides. Okay, يعني when I do the ratio, I will get that V2 over V1, it's 1 minus the linear shrinkage to the power 3, because I have reduction in height by the linear shrinkage and reduction in base dimension by linear shrinkage result. So if you compare the expression of V2 and V1, as you can see here, when you want to calculate V2, you will do H1 times 1 minus 0.013 times 200 times 1 minus 0.013 squared, because the base has equal dimensions. So in total, when you do the ratio of V2 over V1, you will get 1 minus 0.013 cubed. So the volumetric ratio V2 over V1 is 1 minus the linear shrinkage to the power 3. Okay, and this relation will allow you to relate volumetric shrinkage to linear shrinkage. So if in an exam they gave you the volumetric shrinkage during after solidification is this amount, and you want to deduce what is the value of the linear shrinkage, you can use this relation to relate both. Okay? Any question on this problem? Okay. So let us go to another problem. Just here, let us see together in summary the solution of the problem. So first, the first step is to calculate the starting height of molten metal by dividing the initial molten volume by the phase area. We get 25 millimeter. Then, due to volumetric shrinkage given, which is 6%, we calculate the new volume. And since the base dimension is still the same in the first phase, then to find the new height, we divide the new volume after phase 1 by the base area, we get H1. And after this, because of thermal contraction, all sides will be reduced by 1.3%. So each side will be, for the base, it's 200 times 0.987, while for the height, it is 23.5, which is the height just after phase 1, times 0.987. So we get the final dimensions of the plate. Another problem. Now we will solve for problems including Shrobinov's rule, which calculates the solidification time for a mold. We have a disc-shaped part is cast out of aluminum. The diameter of the disc is 650 millimeter, and its thickness is 16 millimeter. If the mold constant is 2.2 seconds per millimeter square in Shrobinov's rule, how long will it take the casting to solidify? So let us draw a figure for the shape of the disc. So we have the diameter of the disc is given. It is 650 millimeters. And the thickness is 16 millimeters. Okay. Now, what we want to do is we want to calculate the solidification time. If we use the Shrobinov's rule, the time of solidification is equal to the mold constant Cm times the ratio volume to area ratio to the power n. Okay. Now, n in general is taken to be equal to 2. The mold constant is given here in second per millimeter square. So the dimensions should be in millimeter to end up with a solidification time equal to second. Now, concerning V over A, V represents the volume of our final cast, V equals to, since we have the shapes are a diameter of 650 millimeter and a thickness of 16 millimeter, okay? So of course here we should take dimensions at the initial state and before solidification, okay? So we have the volume is of a disk is pi r square, so or pi d square over 4. So pi times 650 square over 4 times the thickness, which is 16. Then we get the volume of the part to cast, okay? And for the surface area, we should take the surface area of contact between the mold and the cast part, the molten metal. So A is equal to the lateral area. So we should take all surfaces in contact with mold. So here we have first the two surfaces, the two bases. So I have each base is equal to the area of this circle. So it's 2 times pi r square, or 2. So if you want, it is 2 times pi d square over 4. Pi times d square over 4 plus what we should also take into account, we should take into account the peripheral area here in between the two the circular bases. So we have that the peripheral area here is equal to what? How we can calculate it? This one. What should we do? We should take the perimeter of each circle times the thickness. Okay, so it's plus 2. The perimeter of each part is pi d, so it's 2 pi d, which is 650, times times the thickness, which is 16. Okay, so in this way we calculate the total lateral area, and then we divide V by A and we replace into the expression of the solidification time. So here, as you can see the steps, first we calculate the volume, pi d squared times thickness over 4. Then for the contact area, we have the two area of circles plus pi d times thickness for the second area. And after finding these two, from Shrovinov's rule, we apply the formula that the solidification time is the mold constant times V over A squared. Then we can get the solidification time in seconds. And in case it's needed in minutes, we can divide by 60 to convert it to minutes. Any questions on this problem? Okay. Another problem. The total solidification times of three casting geometries are to be compared. First, we need to determine the solidification time of a sphere of diameter 10 centimeter, a cylinder with diameter and length both equal to 10 centimeter, and a cube with each side equal to 10 centimeter. The same casting alloy is used in all three cases. First, determine the relative solidification time for each geometry, and based on the result of part A, which geometric element would make the best riser? Now, let us try to do it. So first, we want to compare the relative solidification time for three geometries. You know that the solidification time, T total solidification, is equal to the mold constant times V over A to the power N, which is in general 2. Here, why they said the same casting alloy is used in the three cases? Because we are using the same casting alloy, and it should be also mentioned that we are using same same molding properties, same mold metal, and same pouring temperature also. This also should be specified. So since we have same conditions, then Cm is constant. What is variable between the three is the ratio V over A. So the geometry of the riser will affect its total solidification time. So what we will do in this problem, we will try to compare V over A for these three geometries in order to select the best riser. In general, we have two criteria for best riser selection. The first criteria is to have the highest solidification time, because higher is the solidification of the riser, better, because in this way we will ensure that it can solidify after the main cavity. And the second criteria, we should try to minimize the volume. For the same solidification time, if we reduce the volume, it's better. Okay, to not have a lot of waste at the end. So first, we will compare V over A for the three caps. In case we obtain different V over A, then we will select the riser with the highest solidification time. In case we obtain equal V over A, then the best riser will be the one with the lowest volume to minimize it. Okay? To start with, for a sphere, okay, let us calculate the volume and let us calculate the area, lateral surface area. You know that a sphere volume is given by the following formula, which is pi d cube over 6. Okay, while the surface area is 4 pi r squared or pi d squared. Okay, so if you do the ratio for the sphere, you will get that V over A for the sphere is equal to pi will be simplified. You will just have d over 6. D over 6. Okay, so this is V over A for the sphere, and since the diameter here is given, okay, we have it, so it's 1 decimeter, so it's 1 over 6. Okay, so we got the ratio for the sphere. Let us continue with the other types. So we have for the cylinder, okay? For the cylinder, if I know the diameter and I know the height, they are given, okay? So first, if I have a cylinder, to calculate its volume, it's pi d square over 4 times the height. And to calculate the lateral surface area, as we have done in the previous problem, we should consider the lateral area of the two circle at base. And we have the lateral area here of the periphery. So it's 2 times pi d square over 4 plus the perimeter of each circle, which is pi d, times the thickness, which will give us this lateral area. Okay? So first, to calculate the volume, it is pi d square times height over 4. While to calculate the area, it's 2 pi d square over 4 plus pi dl. They gave us the height and diameter to be 1 decimeter. So if we do the calculation, we can find the ratio V over A. And as you can see here, we obtained equal values. So V over A for the sphere of radius of diameter 1 decimeter was equal to V over A for the cylinder of diameter 1 decimeter and height 1 decimeter. So V over A is comparable. Since V over A is equal, is the same, then for the two, the solidification time will be the same. Okay. Now, let us calculate V over A and the solidification time for the cube, for the final shape. For the cube, in order to calculate the volume, of course, it's A cube. It's the dimension of the side cube. So here it's 1 cube, okay? While for the area, it is 6 times the faces. So you have 6 faces here. Each face has an area of 1 square. So in total, the cube area is 6 times 1 square, okay? So you get the value of volume and